Okay, our last chapter. Unless we get done with this really fast and we have time for another one. Or
we get done really fast
or we're
and
too
then party
slow.
the rest of the day.
Or we're so slow that we don't even get to the That would work out pretty good.
That's probably not going to
Or
happen.
we fly through this and then we can watch a movie.
We could find maybe a project.
No.
Or
Are you serious?
Or
That's after that test.
You see
all
that
for
little
the
thing in the
50
corner up there?
Caesars.
That's like no project zone. Like we're in the time zone or something. Yeah, we have too many projects already going on.
Yeah, they're gonna get 5 projects.
There we go. Okay. Sound. We mix sound with vibrations waves because sound is a longitudinal wave.
Waves, bro.
It's because we have compression and rarefaction of air or whatever it
Mr.
is.
Alexander, you are needed in the office. Mr. Alexander, please come to the office.
We didn't go to the office for 5 Alexander.
There's a janitor call.
Uh-oh, it must be an emergency. We should all go.
Okay, so what is sound? What do all the sounds that you hear have in common?
Vibrations.
They're waves, vibrations.
Make noise.
They make noise, yes. How are they different?
They different frequencies.
Different frequencies,
Sounds of noise. Different lengths.
different wavelengths. Okay. Can sounds travel through solids, liquids, or gases?
Yeah.
All three?
Yes.
Which one is better for transmitting sound?
Yes.
Liquid.
Ooh, I hear all of them.
Solids. Remember the train thing we found here?
Solids, it's harder to get to the wall. No, but like if you picture here, you're up to a table and something stands at the table, it's loud. No? So that's like direct.
No, but you'll hear a train sooner if
No,
you
but
put
like-
your ear on the track as opposed to like.
No, but you could hear us really well. But that's not a sound. That's just like if we had like those cups
But
with
what
strings.
sound is?
But I don't know. The cups and strings are solid.
You guys ever been to the Arbor Farm?
Yes.
And they have the whispering bench?
Yes.
Yeah. How's that work?
It's whispering bench.
It's a huge cement, like curved arch bench, and you sit in one little corner, and you whisper in the corner, and then the other person in the way other end can hear it.
Because it travels through
I had those in my house. Well, yeah, but it's metal pipes.
Okay.
Teamwork.
We'll see.
Yeah.
When race cars or emergency vehicles pass you, the sound changes. In what way and why? So as an ambulance is coming towards you, how does the sound change?
Higher pitch.
Gets higher pitched after it passes you. It's higher.
No, it's not. When it's coming
Yeah,
towards
like
you.
what Meyer just did.
What's that called?
Doppler.
Doppler effect. Do you guys know why it's the Doppler effect?
The waves get smushed together.
Yes. Okay, so sound is a longitudinal wave. And what's a longitudinal wave? What's the difference between... And so the particles of the wave move in parallel to the wave. Yep. So all sound waves are produced by vibrating objects like tuning forks, guitar strings, vocal cords, and speakers. They're all vibrating objects. And the vibrating object pushes the air molecules together, forming a compression. So as it comes this way, if this is a tuning fork and it's moving this way, it's compressing the air right here. But then it's going to go right backwards, and it's going to go the other way, and then it spreads them apart, and that's called rarefaction. So you have a compression and rarefaction in a certain frequency. So graphing sound waves. The diagram shows compressions and then rarefactions. So if you measured the pressure or density of the air and plotted these against position, the graph would be a sine wave. So it is a wave. So look at and you know what? I think go.
The vibrating prongs of the tuning fork create a disturbance that travels outward, away from the source of the vibration. When the prong moves to the right, the molecules of the medium are pushed together, creating a high-pressure region called a compression, and represented by the dark region in this graphic. When the prong vibrates to the left, the molecules of the medium are spread apart slightly, creating a low-pressure region called a rarefaction. An alternating series of these compressions and rarefactions move away from the tuning fork. The relative pressures of each region are represented by the sine wave at the bottom of this illustration. When we look closely at the individual particles that make up the medium, we see that they move back and forth in simple harmonic motion. Because the molecules of the medium move back and forth in a direction that is parallel to the movement of the wave, sound is a longitudinal wave.
Yeah. So frequency is the number of waves per second, and so you've heard of ultrasound, right? Yeah, you can do it's for when they check babies, or have you ever had like an injury where they use ultrasound, like in your knee or ankle or on your back? They use it for muscle. It warms muscles. But frequency audible to human ears is between 20 hertz and 20,000 hertz. And so middle C on a piano is 262 hertz, just to give you a reference point. The emergency broadcast signal that you hear on the TV and radio is 1,000 hertz. And infrasound frequencies would be lower than 20 hertz, so ultrasound would be higher than 28,000.
Is there anything that we hear that a lot that's
No. Can you hear an ultrasound? No.
I mean, is there something that
That would be up that higher? I don't know.
because that emergency goes through that's only 1,000.
I don't know. I have a frequency generator. Maybe we'll try getting it out. I don't know where to connect it to. We'll see.
And it will go up to 20.
I don't know what it'll go up to. We'll check it out. I think frequency generator.
Classic.
Yes.
Yeah.
Mhm.
I remember that from like the ACT question, like the graph.
Oh, we have that graph here too.
The average human ear can hear are called audible sound waves. Audible sound waves have frequencies between 20 and 20,000 hertz. Sound waves with frequencies less than 20 hertz are called infrasonic waves. Sound waves with frequencies greater than 20,000 hertz are called ultrasonic waves. Some whale songs are infrasonic. Blue whales, for example, produce songs as low as 2 hertz. For a human to be able to hear this song, it would have to be speeded up 10 times. By the same token, bats commonly use ultrasonic sound in the range of 20,000 to 80,000 hertz for navigation.
Be like where the echolocation stuff.
Like a bat, except that's low.
So pitch is the human perception of how high or low a sound appears to be. And pitch is primarily determined by frequencies. So there are some other factors. Higher frequencies appear to have a higher pitch when played loudly, even though the frequency doesn't change. But it does primarily is determined by frequencies. Like, what did I say, 262 was C?
Yep.
And then so maybe 270 is D or whatever it is. What? Yeah. And then sometimes you can have, we won't go into the cochlea and how you perceive sound. It doesn't, that would be your perception, not the actual sound wave, though. It'd be a human perception.
So like the sound waves the same. It sounds. No, like for tone deaf.
Or have you ever heard, okay, when you hear your voice on a recording versus when you're talking? Yeah.
And you're like,
And that's because the sound wave, you're actually, when you're talking, you can hear that it's in your bones and everything else in your head resonating. And so it sounds different to you when you talk. And then when you hear it on a recording, all you're getting is the air sound.
that's why like.
So it sounds way different.
Because you're eating potato chips, like
Yeah.
resonate.
Because it's, when you're crunching on chips, it's, what?
So do you sound like you're yourself on a recording?
No.
You sound like yourself.
No, not to me. No.
Or do you like to other people?
No, what you hear on a recording is what people hear you as.
Which is really bad because my voice is bad, right?
No.
Like it's annoying. It's annoying. It's annoying just to hear myself talk. But and then it changes, so it's probably got worse.
I wonder what Alex's voice sounds like.
That's actually really weird. Like,
Yep. Anyone's voice is what everyone else hears is what you hear when you listen to a recording
like that's
of
like
yourself.
loud, but actually not like that.
Okay, sound waves can travel through solids, liquids, and gases, and the speed is generally greatest in solid because the molecules are packed tighter together, and so they're able to move quickly through there.
Solids, then liquids, then gas.
Yes.
Yes, I got some. I was the only one that said that. Good job.
How might temperature of air affect the speed of sound waves?
Well, if they were going by how close they are, they wouldn't go
If it's
faster.
faster.
No, it'd be hot because cold
Because
it would be slow,
Yeah.
so it can't travel as fast.
True.
But when it's hot, it's fast, so the sound travels fast. Am I
Correct.
right?
Yes. Higher temperature increases the speed because the particles are moving faster.
Don't get your
Yes. So here you can see air, the speed. Here's the speed of air, of sound in air at different temperatures, at 0 versus 100. And then the different gases are different because helium is a very light gas. It will move faster through helium, which is why when you breathe helium in, you're actually, when you start talking, you're breathing out helium, and helium is going through your vocal cords. And so that's why it sounds faster or higher, because the waves, the frequency has changed because it's not air coming through your vocal cords
What's the
anymore.
one that you breathe that makes your voice go really good?
Sulfur, methane, sulfur hexafluoride or something. I'm not sure. Yeah, on MythBusters when they do that, or there's that video.
I just saw videos of people doing it.
Yeah, I've seen a video of someone doing it.
I've never actually.
But that's not healthy for you at all, right?
No.
So, like, fills up your lungs.
And you're absorbing it, and most of the
And
time,
helium's not good for you.
yeah, it's not good.
Well, it seems like anything kills brain cells.
Yeah.
You look at something wrong, it's like,
There it gives you some different liquids and solids also. Their speeds. What's vulcanized rubber? What's vulcanized rubber? That was on the bottom of that list. Does anyone know? I don't know what the vulcanized means. Make carves?
I feel like most of them is vulcanized.
Oh, what's that mean?
I don't know, it's like something added to it, so it's actually like pliable.
Oh.
Oh, man.
Cannot open specified copy. So sound propagates in 3 dimensions. So if this is your source, like a buzzer or something, it actually goes around and propagates in all directions around that buzzer. Crests or wave fronts. So here would be these are called rays, but the wave front is where there's a peak, and then this would be compression, rarefaction, compression, rarefaction. Wavelength is the distance between those. The rays indicate the direction of propagation. How would these waves fronts appear different if they were much farther from the source? So the farther you get from a source, what do the rays change?
No.
Does the frequency change?
The farther away.
If it's moving away, or if you're moving away from it,
Okay, so
you're standing from it.
standing farther from the source. So the rays will eventually, a reason why it sounds quieter, rays get farther apart from each other because they're coming, like think about if you draw a sun and you draw the rays coming out, they're really close by the sun, and then if you draw them in straight lines, they're farther away, right, on the outside. Same idea there. Okay, Doppler effect. Why are waves closer together on the left? If this is the source of the sound and it's moving, and you are stationary, so the observer looks like is right here, stationary, not moving, but the ambulance is moving towards you. It's moving towards you, and it's basically compressing those waves right here. So it'll be higher. Yes. Right, it'll be louder as it gets closer, but it'll be higher pitch. And then when it's past you, for this observer B, now it's going away, so now it's stretching those sound waves, and so it would be a lower pitch. Now, a lot of times you think of it as gradually getting higher and higher and then dropping, but it really is the gradual part is because of the loudness of the sound. It's just one frequency, and then as soon as it passes you, it drops to a different frequency. Because they tore apart their mannequins.
And we got a lot of cabins.
The Doppler effect, named for its discoverer, is the difference in frequency of a light or sound wave that an observer perceives due to the motion of the source or the observer. Here, observer A will hear a higher pitch than the ambulance driver. Observer B will hear a lower pitch than the driver. Let's see what happens if the ambulance is sitting still. Notice that sound waves traveling from the ambulance reach the two observers with the same amount of time between each wavefront. Now watch closely as the ambulance moves away from one observer and towards the other. Observer A hears wavefronts arriving very close together in time. Wavefronts that arrive closer together have a higher frequency. Observer B hears wavefronts that are spaced far apart. Wavefronts that arrive farther apart have a lower frequency. This accounts for the higher pitch you hear when an ambulance is approaching, and the lower pitch you hear when it is traveling away from you.
There we go. So now what do you think? What is sound? Vibration is what kind of wave? Longitudinal. The one thing that we were in disagreement about was solids, liquids, and gas. It travels through all of them, but solids are better for transmitting.
How can I be talking and no one will be able to hear me at all?
No, it's like if you were.
Someone like talk to the door.
You'd have to be like right next to the door. And right next to
It's
you.
kind of like absorbed in the
It travels faster through liquid. She must not have heard it.